Section 15.4, electrical energy from oxidation reduction reactions. So this is where we're going to be calculating the voltage, because what we're doing here is we are building batteries. I haven't mentioned that yet, but that's what we're doing. We're transferring electrons. We're going to eventually make those electrons travel along a wire so we can make those electrons do work for us. So we're creating batteries. All right, so go and check out video problems. Ooh, I'm going to cross them out here. Go and check out video problem 96 through 98 after we talk about some of this stuff. All right, so first let's talk about what an activity series is. Honestly, activity series is a dated concept. The way that it works is here. These things oxidize very easily, so they give away the electrons very easily. These things reduce very easily. Right? So if these guys oxidize very easily, these guys reduce very easily, then that means that if this oxidizes very easily, it doesn't reduce, and this means if it reduces very easily, it doesn't oxidize. Okay? So basically, the metal, right, will react with the ion that's below it. And that's the way an activity table works. Now, I don't particularly like activity tables because you need the activity table right there in order for you to do anything, as opposed to voltages or electromotive force, which is a little bit easier to deal with. Right? But let me show you what we're talking about here. So here's zinc. When I put a chunk of zinc into a solution of copper 2+, let's identify these. Here's zinc. Here is copper 2+. Right? So when I put zinc and copper 2+, they will react. Right? The zinc will lose electrons, oxidation, so the zinc will be oxidized. The copper 2+ will be reduced, so I'll get this reaction going to copper. And so I'll form zinc 2+ and copper. So maybe I should amend this. The metal will react with the ion below it. The let's say this. So I mean that's fine, but let's say the metal will reduce the ion below it, and vice versa. The ion will reduce or will oxidize the metal above it. Okay. So now take a look at copper solid. Where's copper solid? Take a look at copper solid, and then zinc 2+. So copper solid is lower down in the activity table. It will not cause reduction in zinc 2+. Okay, so that's why there's no reaction. Let's introduce this idea of spontaneous. Okay, spontaneous means that it's going to occur without external energy. A redox reaction, a reduction oxidation reaction, is spontaneous. So it will occur without external energy. Now, what that means for us is that it means a redox reaction that works will always have a positive voltage. And you'll see that once you go look at the video problems. Okay? Now, I draw voltaic cells for you in the video problems, so just sort of read over these notes. I'm not going to read them to you. Read over those notes, and then when I go through the video problem, I'll make sure that I mention these notes specifically. All right? So here's the idea of a voltaic cell. So what you have is, in this case, this is oxidation, right? The oxidation goes in the anode. Anode and oxidation. Ooh, that's a Q. Anode and oxidation both start with a vowel. So that's how I always remember what happens in the anode. Now the cathode, which is this other one, has reduction, the reduction reaction. So here is zinc going to zinc 2+, which is the oxidation reaction. Here's copper 2+ going to copper, which is the reduction reaction. Okay. Now, as long as I have a chunk of metal that will work in the reaction, I use that chunk of metal as an anode, right? Here, copper, zinc, both pretty common metals. But if I have either a metal that isn't too common or no metal at all that can be used as an electrode, then I use inert electrodes. Okay? All right. Now, here we have a wire that's connecting these two half cells, and the electrons travel along the wire. Electrons always flow from anode to cathode. Remember that. Electrons always flow from anode to cathode. Okay? And then finally, we need a salt bridge. And the reason why we need a salt bridge is because as these electrons flow, let's imagine that salt bridge isn't there. As these electrons flow, this beaker is becoming increasingly negative. Right? And then this beaker is becoming increasingly positive. Well, electrons won't continue to flow if that's the case. Right? We'll short out quickly. So what we need to be able to do is we need to be able to introduce something, i.e. salt bridge, that's going to be able to balance out that charge. And so the salt bridge is always an ionic compound. In this case, it's sodium sulfate. Right? The cation, which is positive, goes to the cathode. The cation goes to the cathode to balance out that negative charge. The anion, which is negative, goes to the anode, again, to balance out that charge. And I draw one of these in the sample problems, and then I also go over line notation. All right. Don't worry about all this battery stuff. Look over it; it's pretty interesting, but it's not anything that you need to memorize or anything like that. All right.